All right, welcome back, everybody. Today we're going to be doing section 6.8, which is all about indeterminate forms and L'Hopital's rule. So I know some of you have been anxious to get to this section probably since Calc 1, because I know a lot of times they will teach L'Hopital's rule in Calc 1. But we save it until Calc 2 here at SMC because we use the late Transcendentals version of Stewart's book. All right, let me go ahead and pull up the slides and we'll get started. All right, so this is section 6.8. This is the last section of chapter 6, and then we'll be going on to chapter 7, which is all about integration techniques next time. All right, so here's the overview. We're going to talk about indeterminate quotients first, and then we're going to talk about L'Hopital's rule itself. Actually, one second here. There we go. Then we're going to talk about L'Hopital's rule itself. Then we're going to review an important limit property. Then we'll talk about indeterminate products, differences, and powers, and then that'll be it. So let's get started. So we're going to begin with a motivating example here, and let's just think about this limit for a minute. The limit as x approaches 1 of the function ln of x over x minus 1. And the thing to notice here is that when x goes to 1, natural log of x goes to 0. And when x goes to 1, x minus 1 also goes to 0. So what's happening here is that you've got a limit where the limits of the numerator and the denominator are 0 and 0. So because of that, you actually can't use any of the elementary limit laws that you learn in Calc 1. If you go back and you look at those sections from the book or just look up the information anywhere you'd like, you'll see that you can't actually use the quotient limit law without the denominator not being 0. So we can't use the basic limit laws at this point. But the numerator and the denominator are both going to 0. And so when you have that situation, we call that an indeterminate form of type 0 over 0. So more specifically, if you've got the limit as you approach a point of this ratio, where the top and the bottom are going to be 0, or if you're approaching plus or minus infinity and the top and the bottom are going to be 0, then we call that an indeterminate form of type 0 over 0. And here's the thing, that limit may not exist. So we have some subtleties to address here before we go forward with it. All right, next we're going to consider this one instead. So what if it's the same function, but now let's take the limit as x goes to positive infinity. So now in this case, the numerator is going to go to infinity and the denominator is going to go to infinity, mainly because infinity minus 1 is still going to be infinity. So in this case, we have an indeterminate form of type infinity over infinity. And just like with the previous example, the limit may not exist, so we can't say what it is outright, and that's why we call it an indeterminate form of type infinity over infinity. So these two forms, the 0 over 0 form and the infinity over infinity form, those are called indeterminate quotients. All right, now we have some important notes about this. For one, I have to say this, and I need to be very clear about this. The symbols that you see here, the symbols 0 over 0, infinity over infinity, negative infinity over infinity, infinity over negative infinity, and negative infinity over infinity are not real numbers. These are not real numbers. So you need to be very, very careful when you're using them because these are not numbers and you can't play with them as if they are numbers. In particular, it's not valid to use the equal sign and say that a limit is equal to these symbols. That's not valid. That's not valid because these limits are not real numbers. So these are quite literally just symbols that we've adopted so that we can quickly refer to limits of this type, limits of this form, indeterminate form 0 over 0 or infinity over infinity. It's basically a shorthand because we wanted to be able to refer to these things without having to say it that way over and over again. And that's actually why we call them indeterminate forms. And this is where things get really interesting because you might be tempted to think that something like infinity over infinity is going to be 1, but that is not always the case. So notably, the results of these indeterminate forms may not be 1, or they may be, or they could be any other number, or they could be infinity, or they could be negative infinity, or they could not exist at all. So whatever this limit becomes, if it even exists, we really can't tell outright. And that's why they're called indeterminate. Indeterminate, meaning we can't determine them outright. So the only way we can figure out what these limits really are is through further investigation. And that's what you have to do, investigate further and see what happens. But one thing that can make dealing with these types of limits easier is something called L'Hopital's rule. So here is the big theorem of the section. Suppose f and g are differentiable, and g prime of x is not 0 near a, except possibly at a. We don't need to worry about at a in this case. We're also going to suppose that the limits of these two functions as you approach the point a are both 0, or they're going to be plus or minus infinity, plus or minus infinity. So if you have any of the situations we had in the previous two examples, the motivating examples, then this limit that we're referring to, is an indeterminate quotient of type 0 over 0 or infinity over infinity. And the big result here is that it turns out that the limit as x goes to a of the original ratio is equal to the limit as x goes to a of the ratio of the derivatives, if this limit exists, or if this limit is plus or minus infinity. So that's actually a really, really helpful result. It's a pretty powerful result. So let's kind of look at it for a minute and explain what's going on. So this says that the limit of the quotient, the original quotient that you start with, is the same as the limit of the quotient of the derivatives of the numerator and the denominator. So in other words, if you wanted to compute this limit and you had an indeterminate form of type 0 over 0 or infinity over infinity, you could differentiate the numerator and the denominator separately and compute that limit instead. So that's pretty nice, right? Because maybe there are some functions that are quotients that you've seen in the past where the limit was kind of hard to get to and you had to use some pretty gnarly like arguments to get the limit or to evaluate the limit. Now it's saying, hey, if you happen to have one of those two indeterminate forms, just differentiate the top, differentiate the bottom, and then try to take that limit instead. So that's pretty cool. We're going to use it in just a moment here. One thing I want to say is there is a limitation here. So even though this sounds like like, a miracle, like, oh, this is so easy to do, we are assuming some pretty heavy things. We're assuming differentiability. In particular, L'Hopital's rule only works when the numerator and denominator are differentiable near that number a. So you're requiring differentiability, which is already a strong requirement. I mean, if you've got differentiability, you also have continuity. But we only need this to hold near a. That's one extra little helpful detail here because we're trying to take a limit. And remember, limits are not just evaluation buttons. They're taking limits as you approach a point, right? As you approach a point. Okay. Now, this other important note at the bottom here I wanted to emphasize because I noticed that students tend to forget about this when we get to some of the other indeterminate forms, but L'Hopital's rule cannot be used unless you have one of those two indeterminate forms. So it's got to be 0 over 0, or it's got to be plus or minus infinity over infinity. So when we talk about the other indeterminate forms, I just want to emphasize that you cannot just differentiate the pieces of those things and take the limit. It doesn't work that way. You have to massage things until they're in one of these indeterminate forms. And we'll see that when we get there. But for now, let's let's do a proof first. So I am making a pretty bold claim here that you can just differentiate the numerator and the denominator and the limit will be the same. That's a pretty bold claim. So let's prove it. We're going to prove a simpler case just to save a little bit of time. We're going to prove the case where f and g are continuously differentiable at a. So what that means is that these functions are differentiable and their derivative is also continuous. So in other words, f prime is continuous and g prime is continuous at this number a. All right. We're also just going to assume that the indeterminate form is of type 0 over 0. But again, this proof can be modified and changed to address any of the indeterminate forms that we saw a moment ago, any of those quotients. And you don't need to require continuous differentiability. All right, so here we go. Let's suppose f and g are continuously differentiable at a, and that f of a equals g of a, which equals 0. And that makes sense because what we're saying here is, since f and g are already differentiable at a, that means they must be continuous at a as well. And so the limit as you approach a of f has to be f of a, and the limit as you approach a of g has to be g of a. But since we have an indeterminate form, those both need to be 0. They both need to be 0 because we're using this indeterminate form here. We're also going to suppose that g prime of a is not 0, so that way we won't have to worry about any division by 0 issues when we compute the derivative. All right, so here we go. We're going to use one of the most important techniques in mathematics. There's two, if you remember. There is multiplying by 1, and then there is adding 0. So in this case, we're going to add 0, but we're going to do it twice. So here we go. this limit, the limit that we want to evaluate, is equal to this limit right here. And all I did was just subtract 0 from the numerator and the denominator. That's the clever bit right there. Then we're going to rewrite this 0 as f of a and this 0 as g of a. Because again, these values are equal to 0 at a. So we can substitute that, right? We have this, so we can substitute. Okay, now we're going to use the second most powerful technique in mathematics. We're going to multiply by 1, but we're going to multiply by a clever one. So namely what we're going to do is we're going to multiply the top and the bottom, the numerator and the denominator, by 1 over x minus a. So basically multiply this piece by 1 over x minus a, and then multiply this piece by 1 over x minus a. 1 over x minus a divided by itself is 1, so we're allowed to do that, and we haven't changed the value of anything. But now here's the cute part. So look at the numerator here, f of x minus f of a over x minus a, g of x minus g of a over x minus a. That structure looks really familiar, and I hope you recognize it as the difference quotient. And now we can actually apply the quotient limit law and move the limit into the numerator and denominator of the big fraction, specifically because we assumed that these two functions are differentiable at a. Because now what do we have here? So this is the difference quotient. What is this thing right here? Well, that's the derivative. That's the derivative of f at a, just by definition. So this is f prime of a, and this is g prime of a, and that's what we have down here. F prime of a over g prime of a. But remember, we also assumed that the derivatives of f and g are continuous, right? So f prime of x and g prime of x are both continuous. And so that means by definition, f prime of a is the limit as x goes to a of f prime of x, and g prime of a is the limit as x approaches a of g prime of x. There we go. Now using limit laws again, we can pull the limit operator all to the front of this quotient, and we have our result, that the limit of the original quotient is equal to the limit of the derivatives. Pretty cool stuff. Cool stuff. So again, I encourage you to go through this proof and think about it and look it over. It's actually a very cute and pretty clever proof. We do need everything that we assumed here. So I encourage you to go back through and just follow all the steps to see how we got that result at the end there. All right, that being said, let us talk about a geometric interpretation. So we basically did an algebraic proof, and we have this idea, but sometimes it's easier to see things when you have a picture. Like, why is it that the limit of that original ratio is equal to the limit of the derivatives, right? So if we think about the fact that, or let's just assume that our function is differentiable at the point, then that means that it has a linearization at the point. So if you recall from Calc 1, or even from the review that I did earlier, we can talk about the linearization of these functions at the point a. And a linearization is just a linear approximation of that function at the point a. And so here's the linearization of f, here's the linearization of g, and we can basically look at the limit of these linearizations instead. So here, the limit as x goes to a of f of x and g of x is equal to the limit as x goes to a of the linearizations of f and g. In particular, because these things are continuous there. They're continuous at a. Now, because they're just lines, right? Lines are continuous. Now we're just going to substitute the formula for these linearizations. There we go. But remember that f of a is equal to 0, and g of a is also equal to 0 because we have the indeterminate form 0 over 0. So then when we substitute those, we get this. And then now we're left with this expression, and because we're taking a limit, we know that x is not equal to a for these things. So we can actually cancel this, this factor that's equal to 1, and then we're left with this. So there's another way of seeing it in terms of linearizations. What does the picture look like? The picture looks like this. So here's the function f, here's the function g. The limit as x approaches a for these functions is 0 for both. So f goes to 0 as x goes to a, and g goes to 0 as x goes to a. So we have 0 over 0, right? Here are the linearizations of those two functions. Those are the linear approximations at a, right? So this is basically the tangent line approximation right here. That's what you're seeing in this picture. And what you can see is that, again, these are going to have the same limit. And so from that, you can get that the derivatives have the same limit, the ratio of the derivatives. All right. Okay, so in practice, L'Hopital's rule is actually very fun. So I hope you enjoy it as much as I do and as much as my students tend to. Let's use it now, and we'll see how fun this can be. Now let's find this limit. So we need to establish a few things first. What I want you to do is I want you to actually think about it for a minute and just ask yourself, what do you need to establish first before we can use L'Hopital's rule? Think about it for just a moment. Okay, now say something out loud to yourself. What do you think you're going to need to use before, or what do you need to establish before you can use L'Hopital's rule? Say something out loud. Okay, now let's do this one together. So here's the first couple things. We're going to label the numerator f and g like so. First, they're both differentiable near the number 1. So that's the first thing that we need to establish. Remember, when we say near a number, what we mean is on an open interval that contains the number, but not necessarily at the number. So the number 1 is in an open interval, and on that open interval, both natural log of x and x minus 1 are differentiable functions. Okay, so there's that first. The other important point is when we compute the derivative of the denominator is just, hold on a second, is that negative 1? No, no. Negative 1, I think that should say 0. Hold on a second. Yeah, sorry, that's a typo right there. That should not say negative 1. If this is g of x down here, then g prime of x is going to be equal to 1. Yeah, so I'm sorry, this should say positive 1. I'll change that in the slides later. That should say positive 1. But the important point here is that the derivative of g is not 0 when you're near 1. There you go. It's not 0 when you're near 1. In this case, the derivative of g is a constant function. It's just the number 1. All right. Now, so we've established that differentiability, non-zero, lower derivative near the point 1. And then lastly, we actually do have an indeterminate form of type infinity over infinity. Why is that? Because the limit as x goes to, oh wait, nope, that should say 0 over 0 as well. Oof, couple typos, I apologize. This one should say 0 over 0. I'll change those in the slides after I finish this recording. So let's see, right? Yeah, because when it goes to 1, ln of 1 is 0. Yes, 0 over 0. Oi. Okay, so the three things. It's differentiable near the point. The derivative of the bottom is not 0 near the point. And the indeterminate form is of a form that we can actually use. It's 0 over 0. Now we can apply L'Hopital's rule. So here we go. Just like so, we're going to differentiate the top. As we saw before, the derivative of natural log is 1 over x. And like I mentioned a moment ago, the derivative of x minus 1 is just 1. And a lot of times when we employ L'Hopital's rule, and you should get into this habit too, we will indicate as such using a little L apostrophe H. L apostrophe H. So when you're writing your limit calculations, you need to use that to indicate that you just executed L'Hopital's rule between these two steps. And that's what we did. So we differentiated the top, got 1 over x, differentiated the bottom, got 1. So now we're just looking at the limit as x goes to 1 of 1 over x. And this is great. This is a limit that we can simply evaluate by direct substitution because 1 over x is continuous at 1. So we can substitute 1 in and we get 1 over 1, which is equal to 1. Yay! All right. So now this limit that we were unable to approach before, we made pretty short work of just by differentiating things and looking at the limit of the derivatives. There we go. Okay, let's do another one. And this one I want you to try on your own in the beginning. So this is the limit as x goes to 0 of tangent x minus x over x cubed. And so I want you to think about it first. And again, what do you need to establish in order to use L'Hopital's rule? Think about that for just a moment. All right, now say something out loud to yourself or to the wall or to your dog or your cat or your friends, your family. Say something out loud, give your brain that feedback. All right, now try it on your own. So try to work this one out on your own. See if you can find the limit, and then we'll do it together in just a moment. All right, let's do it together. So let's see. First, we need to establish that the numerator and the denominator are differentiable near zero. So we need to establish that. We need to be sure that the derivative of the denominator is not zero near zero. And then we need to establish that we actually have an indeterminate form. So here we go. So the numerator we're going to call f, the denominator we're going to call g, and these are both differentiable near zero. They're just continuous functions, right? And we also know that the derivative g of x, or sorry, g prime of x, which equals 3x squared, is not zero near zero, not zero near zero, right? I know that sounds kind of funny, but remember limits are taking values or we're approaching a number, right? So as we're approaching zero, g prime of x will not be zero. It will only be zero at the number zero itself. A lot of zeros being thrown around. Also, we have an indeterminate form of type 0 over 0. So again, as as x goes to 0, tangent goes to 0. So we do have 0 over 0. Now we can apply L'Hopital's rule. So we hit it with L'Hopital's rule, bam, and we get this. This is our new limit. Secant squared x minus 1 over 3x squared. And now if you got to this point when you were doing it on your own, that's perfect. That's great. But then you should have hit a little bit of a snag because you should have realized, well, wait a minute, this is still going to 0 over 0. It's still an indeterminate form. The limit of the denominator will be 0, and the limit of the numerator is also going to be 0 because secant of 0 is 1, and so secant squared of 0 is 1, and 1 minus 1 is 0. Okay, but here's the best part about L'Hopital's rule. You can continue to apply it as long as you're satisfying those three conditions: differentiability near, non-zero near, and a proper indeterminate form. So what we're going to do again is we're going to apply L'Hopital's rule to this new limit and continue the calculation. And it turns out you can apply L'Hopital's rule as many times as you want, as long as the conditions are satisfied. So here we go. Whew. All right, got to take a breath, dive in here. We applied L'Hopital once to get this result. Now we're going to apply L'Hopital a second time. And when we do that, we've got to use the chain rule on secant squared. And so we get this as our numerator, and this is our denominator. But once again, if you look at this and you try to evaluate this at 0, you're still going to have 0 over 0. So you have this 0 over 0 form. Differentiability is still good. Non-zero near at the bottom is still good. Apply L'Hopital again. And now you've got to apply L'Hopital. I'm sorry, now you have to use the the chain rule and the product rule. So this derivative is a little more intense. But we're making some progress. We're making some progress because if you look at the denominator, the derivatives keep approaching a constant term, right? A non-zero constant term. So when you differentiate 6x, you just get 6. This is really nice because that means the denominator is not 0 anymore. So maybe we'll be able to evaluate the limit. In fact, we can, right? Because you don't end up with any sort of indeterminacy in the numerator. Now we've gotten to a point where we can just do direct substitution. Now we have something that's continuous at 0, so we can plug it in. So we plug in 0 for all of these x's, and we get this. 2 times 0 plus 2 times 1 times 1. The denominator is still 6, and so we get 1/3. Yay! Okay, so one thing I want to point out here, again, like I mentioned earlier in the slides, this limit was not 1. This limit was not 1. So even though in the previous example, that limit happened to be 1, here we have an indeterminate form 0 over 0, but the limit is not 1. The limit is actually 1/3. So this is why they're called indeterminate forms, because we don't know what the limit is until we investigate further. And L'Hopital's rule is a good way of figuring out just what's happening. All right, so 2 good examples. Now let's move on to indeterminate products. So we talked about indeterminate quotients, and now we've got this really helpful tool called L'Hopital's rule. And we can leverage it. We can leverage it to help us evaluate limits that are a different kind of indeterminate form. So now we're going to look at one of those. We're going to look at indeterminate products. So here, let's suppose that the limit of the function f of x is 0 as you approach a, and the limit of g of x as you approach a is plus or minus infinity. Then the reality is that it's not clear what the limit of the product is going to be. What's the limit of f of x times g of x? It's actually not clear what that limit's going to be. And so we call this an indeterminate form of type 0 times infinity, or 0 times negative infinity. All right? Okay, this is going to sound like a repeat, and frankly, a lot of it is just copy and pasted, but just like before, I want to mention and emphasize that these symbols are not real numbers. So when you write something like 0 times infinity, we're not talking about 0 times infinity being a number and talking about the result. These are just symbols that we adopted to be able to easily talk about indeterminate forms of this type. So we want to be able to say, hey, the limit of this function as x approaches a is 0, and the limit of this function as x approaches plus or minus infinity is infinity, or sorry, as x approaches a is plus or minus infinity, and we want to look at the limit as x approaches a of the product of those two things. Like, we don't want to say that all every single time. We would like to be able to just say infinity times, or 0 times infinity. That's the form we have. But I just need to emphasize, it's not valid to use the equal sign and say that a limit is equal to these things. That's not the reality. That's not the case. These are just symbols that we've adopted to refer to these things. And again, these are indeterminate forms. So notably, and maybe this will come as a surprise, I would love to talk more about it in the activities, but the results of these indeterminate forms may or may not be 0. So when you see something like this, I need to emphasize that this is not equal to 0. Not necessarily. And it also doesn't make sense that to say something like this is equal to 0, because infinity is not a real number. If you want to talk about transfinite arithmetic, you have to set up a lot other background foundation to make sense of it and to develop a consistent mathematics around it. We don't have that right now. We don't have that right now. So hopefully I'll be able to convince you in this class that when you see something of this form, it may or may not be 0. May or may not be 0. So we will see. What do we have to do in this situation? We can't just claim that it's 0. We have to go through further investigation, and L'Hopital's rule will come to the rescue. So if we're going to use L'Hopital's rule, what we need to do is we need to review or address an important limit property. And what I'm hoping is that your pre-calculus instructor talked to you about this at some point. I know that I do very explicitly in my pre-calculus classes, specifically because it's a technique that comes up over and over and over again in calculus and just analysis in general. So here's what it is. Let's look at the limit as you approach a point from either side. If the limit of your function f of x is infinity at that point, then the limit of the reciprocal of that function is going to be 0. And this is an if and only if statement, so it goes both ways. In other words, if you've got an infinite limit as you approach a point, then the limit of the reciprocal at that point is going to be 0. And essentially this is happening intuitively because of this. If you're going to infinity as you approach a point, and then you reciprocate all of the results, or reciprocate all of the values as you approach that same point, then your denominator is going to be getting very, very large. And so that means that the entire function is going to be getting very small, and it's going to go to 0 in the limit. That's really what it is. So actually, maybe I'll do this for a minute. Let me throw the thinker up on the screen, and I just want you to read this a couple times and just think about it. And then I'm going to do an example involving cosecant. Okay, so let me give you an example with cosecant. So some of you might remember way back when you were learning trigonometry for the first time that you had to graph functions like cosecant, secant, and cotangent. And the general tip for graphing those functions is to graph the original function first. So not the co-function, but the original function. And then you kind of just do these little like parabola-like things at each of the peaks and the troughs. So maybe this will refresh your memory a little bit. Let's do sine. Okay, so here's the sine curve. Oops, it's harder to go backward for me. There we go. There we go. So this is basically sine of x. And if you wanted to draw cosecant, right, the reciprocal of sine, then what you usually do is you put these things, you put some like little loops right here and right here. Sorry, not loops, parabola-like things. And there's a reason for that. There's a reason for that because you remember that cosecant actually has asymptotes. So let me put in the asymptotes first. Here's one, just like so. Here's a bunch more. So you'll have asymptotes at all of these points. And then what is your function? Let me pick a different color like green. There we go. Let's draw cosecant. So cosecant will look like this. There we go. Right. So maybe this looks a little familiar. Well, the reason I wanted to draw your attention to this graph is because the reason that the graph looks this way is because of this important limit property. Literally what's happening is this. So we're just going this way to this way, or really the other way. So think about it like this. Okay, as sine approaches this value, this is the value pi, right? So as sine approaches pi, or sorry, as x approaches pi, sine approaches 0. So basically the limit as x approaches pi of sine of x is 0. So what that means is that the limit as x approaches pi of the reciprocal is going to be infinity, depending on which side you approach from. So I should say plus or minus. It's going to depend on the side you approach from. But that's exactly what happens, right? So 1 over sine is cosecant. And as x approaches pi, cosecant goes to positive infinity or down to negative infinity. Because what happens is reciprocation at a point reverses the limit behavior at that point. That's exactly what happens. So that's how you draw these graphs. That's really why it's working. And you can see it's the same for every 0 of the sine function. Everywhere sine is 0, cosecant is going to have a vertical asymptote because the limit is going to be infinity when you reciprocate. That's it. That's the idea. Okay, so consider that idea that the reciprocation switches a limit that is infinite to a limit that is 0. That can be pretty handy. Let's see how. If we want to do if we want to evaluate an indeterminate product, we're going to be clever. And what we're going to do is we're going to write that product as the quotient of a reciprocal instead. So here, f times g is the same as f divided by 1 over g, right? Because if you flip and multiply the denominator, you'll get f times g again. Or you could rewrite it like so, g over 1 over f. And these are equalities, so that product is just being massaged and rewritten in a nice way. And because we have that important limit property, we know, for example, that if g of x goes to infinity, then 1 over g of x is going to go to 0. And so now what we can do is we can convert that indeterminate form, 0 times infinity, into the form 0 over 0 or infinity over infinity, and then apply L'Hopital's rule. Pretty cool, huh? Pretty cool. It's a clever idea. Let's try it. Okay, so we're going to do this one, and I want you to try this one on your own. See if you can do this technique on your own, and then we'll do it together. So as usual, think first what you would have to do before you can apply L'Hopital's rule. How would you rewrite this product as the quotient of a reciprocal? Think about it for a minute. All right, now you got to say something out loud. Just say something out loud how you would write this as the quotient of a reciprocal. All right, and now try to do it on your own. See if you can compute this limit, and then we'll do it together. All right, here we go. So first, we're going to note that it is actually of an indeterminate form. So this is a 0 times negative infinity form because the limit as x goes to 0 of x is 0. And the limit as x goes to 0 of ln of x is negative infinity. Notice also that we're only approaching from the right. And that's because the natural log function is not defined for, it's not defined for non-positive numbers. So we can only approach 0 from the right within natural log's domain. Okay, so we do actually have this indeterminate form. And because the limit as x goes to 0 of x is 0, that means that using that important limit property, the limit of the reciprocal is going to be infinity. So 1 over x goes to infinity as x goes to 0 from the right. Now what we're going to do is we're going to rewrite x times ln of x as natural log of x divided by 1 over x. And that's all we needed to do because, again, now we have infinite or negative infinity over infinity. Ta-da! Now we can use L'Hopital's rule. So we've got an indeterminate form that's approachable with L'Hopital, so let's use it. Boom. Rewrite our limit. Use L'Hopital. Oop, oh no! Bad typo right here. This should say limit. This should say limit as x goes to 0 from the right. Don't forget your limits. Don't forget your limit operators. Oh wait, oh sorry. I wanted to include it like this. Come back, come back. This. Okay, this should say limit as x goes to 0 from the right. Pretend it's there. All right, now we can simplify things a little bit though, right? So we can't just take the limit outright because we would still have a, what is that, an infinity over infinity situation. But look, we can simplify. 1 over x, oops, now I want to use this for that. Here we go. 1 over x divided by 1 over x squared is equal to x squared over x, which is just going to be equal to x, or negative x in this case because we have that negative as well. So this is the new limit, and now in this case it is 0. We can take that limit. The function negative x is continuous, so we can use direct substitution. All right, so you'll see some more of these on the homework, but now let's talk about indeterminate differences. This one is actually one of my favorites, although the techniques aren't that exciting. But it's a fun one to think about. So let's say you have two infinite limits. So the limit as you approach a point is infinity for either of these, then again, what happens here is not clear. The limit as x approaches a of the difference is an indeterminate form. It's an indeterminate form of type infinity minus infinity. And really what I'm trying to say is that infinity minus infinity may not be 0. I'm not going to repeat the slides from before, but again, infinity minus infinity may not be 0, and it turns out that it could be any number. It may not even exist. So you can play with these things in all sorts of ways, and depending on what the function is, you may not get 0, you may get something wild, you may get a limit that doesn't exist, you may get infinity. There's all sorts of things. And maybe to give you some intuition, this is what I usually like to do. Think about this. We'll talk about infinity minus infinity for a minute. Let me draw a sketch. Think about the graph of this parabola. Okay, and my question to you is, what's the area above this parabola? What's the area? Think about it for just a moment. Let me throw up the thinker for just a moment. What's the area? It's not a trick question. All right, yeah, it's infinity, right? The area is infinite. There's infinite area above that parabola. Now think about this parabola instead. What's the area above the green parabola? Infinite, right? It's got infinite area again. But intuitively, you could say that, or you can see that the area above the green parabola is more than the area above the blue parabola. So if you were to do infinity minus infinity, you shouldn't get 0 because there's quote unquote more area above the green parabola. So that's why these things are indeterminate. When you start playing around with indeterminate forms and when you start playing around with infinity, things don't behave intuitively anymore. You have to be very, very careful. So to do that, you have to develop transfinite arithmetic, and that's exactly what George Cantor did back in the late 1800s and early 1900s. So we can't do infinity minus infinity. That's what I'm trying to say. We cannot do it. And again, this is just a limit. This is not, it's not actually plugging in infinity because infinity is not a real number. We're taking limits. So how do we deal with these things? We're going to jump right into an example to see how this works. The techniques aren't as clever as the last one, I must admit. So here, how do you think we would evaluate this limit? Just think to yourself for a second and see if you could figure out how you would try to evaluate this limit. All right, now say something out loud to yourself and see if it makes sense. What would you try to do first? Okay, now let's do it together. first thing is we can't use linearity of the limit operator, and we can't just do the limit of the individual ones because this limit doesn't exist. It's an indeterminate form, so you can't just throw the limit operator into each term. But what we can do in this case is we can actually find a common denominator, and maybe that'll help. So that's what we're going to use in this case. We're going to rewrite secant x minus tangent x as 1 over cosine x minus sine over cosine x. Because now this might actually get it into a quotient, into the form of a quotient, where it'll be indeterminate, and then we could use L'Hopital's rule. All right? One other thing I want to add before I proceed is this. In other cases, multiplying and dividing by a conjugate can help. So I don't include an example of this here, but I do include an example of it on the activity. But just keep in mind that if you have an indeterminate difference, multiplying and dividing by a conjugate can be one approach that works. Again, you're just multiplying by one, but you're multiplying by a clever one, and that clever one happens to be conjugate divided by itself. So keep that in mind for the homework and for the activity. Now let's proceed with the calculation. So here, when we rewrite secant and tangent like so, we can combine those two fractions into one fraction. Now we have an indeterminate form, right? So sine of pi over 2 is 1, cosine pi over 2 is 0, so we have an indeterminate form 0 over 0. That's what we get in this case. Since we have one of those indeterminate forms, the numerator and the denominator are differentiable, the denominator is not 0 near pi over 2, we can use L'Hopital. So we use L'Hopital, differentiate the numerator, get negative cosine, differentiate the denominator, get negative sine. So now we can actually check again. Can we evaluate this limit? Well, let's see. Sine of pi over 2 is 1. Great. So the denominator is not 0 anymore. We don't have any indeterminacy in the numerator anymore. We can just use direct substitution. Now we can take the limit. We'll get 0 over 1, which is equal to 0. Hooray! So in this case, we did get 0. Nice. All right, moving along. Now we talked about indeterminate quotients, indeterminate products, indeterminate differences. Now we're going to finish up with indeterminate powers. So there are several indeterminate forms that arise from these types of limits. So if you want to take the limit as x approaches a of one function to the power of another function, there are a few indeterminate forms. 0 to the 0. In this case, f of x goes to 0 and g of x goes to 0, so you're getting 0 to the 0. Another indeterminate form is infinity to the 0. So in this case, you would basically have f of x goes to infinity and g of x goes to 0. And then the last one is 1 to infinity. So now f of x is going to 1 and g of x is going to infinity. And those are the three indeterminate powers. The other combinations are actually not indeterminate. So I encourage you to think about that, and maybe we can talk more about it during the activity. But these are the three indeterminate powers that we can work with. These are the only ones that are indeterminate. And how do we do it? Well, maybe not surprisingly, we're going to use logarithms and exponentials. So this is one of the reasons why at SMC, in this book, we wait to talk about L'Hopital's rule until Calculus 2. Because in order to talk about indeterminate powers and use L'Hopital's rule on these powers, you need the exponential and you need the logarithm. And that was something we didn't develop until this chapter. All right, so how do we do it? Well, you've got two approaches in either case. I'm going to do an example of each. You can either use logarithmic differentiation, so take the log of this thing and look at that and see what that does, or you can rewrite the exponential with a base of e. Those will be your two options. Which you choose is up to you. It's very much just like when we learned about logarithmic differentiation, your choice. It's a matter of personal taste. I'll do both just so you can see the difference. Okay, here's the technique. Let's let y equal our exponential. Then if we take the log of both sides, we can say that ln of y is equal to g times ln of f of x. That's just using the power property of logarithms. Now we have an indeterminate product, right? Because in either of these cases, 0 to the 0, infinity to the 0, or 1 to the infinity, this product will now be indeterminate because you're going to have a 0 times infinity situation. That's really what it'll be. Now that you have an indeterminate product, you can write it as an indeterminate quotient, and then you can apply L'Hopital. That's it. Now, instead of doing this technique, what you could also do is just rewrite your original exponential with a base of e, and then you'll still have an indeterminate product. It'll just be in the numerator. Or, I'm sorry, it'll be in the exponent. So then you can just deal with the indeterminate product in the exponent there. Okay, here we go. Let's do this one. This one should look familiar. Limit as x goes to 0 of 1 plus x to the 1 over x. So what indeterminate form do we have? Well, as x goes to 0, this piece is going to go to 1. And then as x goes to 0, this piece is going to go to infinity. So we have 1 to the infinity here. That's the indeterminate form. And again, you might feel tempted to say that when you have 1 to the infinity, it's just 1. But as you can recall, or maybe you'll see here, this limit is not 1. This limit is not 1. Let's see what it is. Here we go. For this one, what I'm going to do is I'm going to use a logarithmic differentiation. So I'm going to write y equals 1 plus x to the 1 over x, take the log of both sides, and pull the 1 over x out using properties of logs. Now I'm going to take the limit of this. So limit as x goes to 0 of ln of y from the right is equal to the limit as x goes to 0 of the other side. Here I'm just rewriting it. So 1 over x times ln of 1 plus x is just this. But now look, now we actually have an indeterminate form that we can deal with, right? ln of 1 is 0, and 0 is 0. So we have the indeterminate form 0 over 0. Boom, we can apply L'Hopital's rule. Apply L'Hopital's rule once, we get derivative of ln of 1 plus x is 1 over 1 plus x. The derivative of x is 1. And so now we're looking at this limit, and in this case, we get 1. All right, now here's where you have to double check yourself. If you're using this technique, don't forget that all we did was find this limit. We found the limit of natural log of this thing. We did not find the limit of that thing itself. So we have not answered the question. So this is one of the subtleties you got to remember if you use this technique. You may have to remind yourself to go back and basically exponentiate everything. So now that we know that the limit of this is equal to 1, we also know that the exponential function is continuous, so we can move the limit operator inside the exponential. In essence, we're going to exponentiate both sides, like so. And when we do that, we'll get this. There we go. Yeah. So here's where I'm actually doing the exponentiation, right? Because e to the ln of y is just y again. And that was the limit that we wanted originally, the limit of this. Now here, from this step to this step, we can move the limit operator into the power because the exponential function is continuous. Then we can just plug in what we know about our limit. We just found that it was 1. So we get e to the 1, which is e. Ta-da! There's that special number. And again, this turns out to be equal to e. It's not 1. So even though the indeterminate form was 1 to the infinity, we did not get 1. We got e. Okay, let's do one more example, and then we'll call it a day at that. Let's find this. So this is actually one of my favorite functions. Actually, one of my favorite functions is absolute value of x to the x, because I think the graph is just absolutely gorgeous. But let's just do x to the x approaching from one side. And what I'm going to do now is I'm going to use the other technique that I mentioned. Rather than call this y and then take the log of both sides and proceed that way, I'm just going to rewrite x to the x as e to the ln of x times x. This thing. There we go. Oh, incidentally, this is a picture of the graph of this one, x to the x. All right. Now we're just going to take the limit like we normally would. So limit as x goes to 0, of x to the x. I rewrote x to the x as e to the x ln x. But again, the exponential function is continuous, so we can move this limit into the exponent, and we get this limit right here. So now we're basically looking at, let me write it right here. We're looking at the limit as x goes to 0 of x ln x. which is an indeterminate product. But you might remember from when we did that example earlier in this lecture, this indeterminate product ends up being 1, right? So we get e to the, oh wait, am I misspeaking here? Hold on, ln of 0 is, oh yeah, you get an indeterminate product. That's right. So then you get 1. So this is a little bit haphazard. I shouldn't really write it like that. Forget that. When we computed this, it ended up being 1. There we go. Hold on a second. Now I'm skeptical. Wait a minute. Let's go back and look at that. What was that indeterminate product? It was 0. Okay, that's where I'm getting all messed up. We found that it was 0. There we go. So the limit as x approaches 0 of x ln of x is 0. What am I saying? Okay, go back. There we go. So this 1 shouldn't be there. You just get e to the 0, which in this case is going to be 1. E to the 0 is 1. Oi, so I got a couple typos to fix. I'll do that right now. Oh, and that should be a plus. All right, but that's it. That's it. So now let's play. I'm looking forward to doing this activity. I can answer your questions during the sessions as well. Um, Thank you for bearing with me on this particular lecture. I know it's one of the longer ones, but L'Hopital's rule is a very powerful technique, and you'll probably have to use it a lot, so it's good to spend some time on it. All right, I'll stop rambling. I'll see you all next time, and thank you for watching.